Let's look at some examples of 2D linear transformations. First off, consider the matrix A equals 2, 0, 0, 2. We'd like to consider what happens to a standard vector in two dimensions. Consider the matrix A equals 2, 0, 0, 2. Let's consider what this linear transformation does to a standard vector in two dimensions, say x, y. Under this transformation, we would multiply our matrix A, 2, 0, 0, 2, times our standard vector x, y, to end up with the vector 2x, 2y. In other words, what has happened is our original vector x, y has been stretched by a factor of 2 in both the x and y directions. This is what's called the dilation. To see what this looks like graphically, let's take an example vector. Let's look at the vector v equals 1, 2. If I plot that original vector in our xy plane, that would look something like 1 unit in the x direction, 2 units in the y direction, and our vector would look something like this. Now under the transformation, if I look at the matrix A times the vector v, this linear transformation would be 2, 0, 0, 2 times my original vector 1, 2. And again, remember, we already showed that we know that will be 2x and 2y, so I'm going to stretch out the x coordinate by 2, so 2 times 1, and stretch out the y coordinate by 2, so 2 times 2 is 4. And if I go ahead and graph that, I would get something like 2 units in the x direction, 4 units in the y. And this is my new transformed vector, A times v. And notice I didn't draw it in the same scale, but our new vector should be twice as long, or dilated by a factor of 2, of my original one. Let's look at another example of linear transformation. Let's look at the matrix B equals 1, 0, 0, 0. Again, let's look at a standard generic vector in two dimensions and see what happens when I multiply by B. So my B matrix is 1, 0, 0, 0. Multiply by my vector, some generic point x, y. And I'm going to get, multiply that out, you get x, and then you get 0. And this is what's called a projection. In this case, I'm projecting onto the x-axis. Again, let's look at what that happens graphically. Let's pick a standard vector to try. Let's look at the vector 1, 2. So in my xy plane, if I consider the vector v equals 1, 2, under the transformation, I'm going to multiply b times v, which is 1, 0, 0, 0, times 1, 2. And if you multiply that out, you just get the vector 1, 0. So that's 1 unit in the x direction, no units in the y direction. And that's my transformation, b times v. And you can see the reason this is called a projection, if you look back into my original vector v, this just looks like a projection onto the x-axis. So imagine just projecting that down. Similarly, you could guess what the matrix that would project onto the y-axis would be. That would be 0, 0, 0, 1. Let's look at one last projection example. Here we've got the matrix C equals 1, 3, 0, 1. Again, let's consider what happens to a standard vector in two dimensions, the vector x, y. Under this transformation would get multiplied 1, 3, 0, 1 times our standard generic point, xy. When I multiply that out, I would get x plus 3y and y. And this is what's called a shear transformation. And if I look at my shear transformation, again, I'm going to pick a vector just as an example. So let's pick the example vector 1, 2. That's 1 unit in the x, 2 units in the y. That's my vector v. Under the transformation, I would get v times the linear transformation C is 1, 3, 0, 1 times the vector 1, 2. And I would multiply that out, you get 7, 2. So that'd be 7 units and 2 units this way. And you see you get a shear transformation here. So that's 3 examples of transformations in 2 dimensions. Thanks.